We're starting chapter 11 with talking about space figures, so 3D objects, and we're going to identify what amount of vertices, edges, and faces they have, and we're also going to use this thing called Euler's formula in order to help us with that. So the first thing we have to do is we have to get some vocabulary down. We have a few words here. First of all, a polyhedron is just a 3D figure whose surfaces are polygons. A face is each side of that polyhedron. So, for example, this would be a face here. This would be a face here. If you think of a box, you're looking at any of the sides of the box. The flat surfaces are the faces. An edge is a segment that is formed by the intersection of two faces. So along an edge here where two of our faces meet, that's an edge. And then a vertex is a point where three or more edges intersect. So like right here, right here, right here, right here. The corners of the box is a vertex. So now we need to go through these examples and see how many vertices, sorry, there's a typo there, how many vertices, edges, and faces are in each of the polyhedrons. So in this first one, I'm going to go ahead and see, I'm going to call them V, E, and F for vertices, edges, and faces. Okay, so I'm going to start with vertices, I guess, because that's my first letter. I've got 1, 2, 3, 4, 5 vertices. Edges, I have the 4 at the bottom, but then I also have the 4 coming up to make the point. So that's a total of 8 edges. And my faces, I have the base, and then I have each of the 4 walls that are coming up on that pyramid. So that's a total of 5 faces. So then you go ahead and try that next example there. We have this thing called Euler's formula. I know it looks like Euler's, but it's not Euler's, it's pronounced Euler's. And the formula says F plus V equals E plus 2, where F, that's faces, V is vertices, E is edges, and then 2, I'm just adding the number 2 to the number of edges that I have. So this question says, how many vertices, edges, and faces does the polyhedron at the right have? Use your results to verify Euler's formula. So I'm going to go through, just like in that last example we did, I'm going to look at this picture and see how many vertices, edges, and faces I have, but then I'm going to plug it into Euler's formula and see if it actually works. So I've got faces, vertices, and edges. It doesn't really matter what order you go in. My faces. Well, I've got the top and I've got the bottom, so that's 2. And then these are hexagons. So I have 1 side, 2 side, 3 side, 4 side, 5, 6 sides. So 6 of my vertical walls here. And then I also have the 2 bases. So that's a total of 8 faces. Vertices, I have this corner here, 2, 3, 4, 5. I have 6 corners at the bottom, but then I also have 6 corners at the top. So that's a total of 12 vertices. And edges, I've got 1, 2, 3, 4, 5, 6. So there's 6 edges there. 6 edges at the top, that's 12. But then I also have these 2, 3, 4, 5, 6 edges going up vertically along my shape. So that was 6 here, 6 here, and 6 here, which gives me 18 edges. So let's see, if I plug that into Euler's formula, I've got F plus V equals E plus 2. 8 plus 12 gets me 20, and 18 plus 2 also gets me 20. So that checks out. I see that that works. So now we're going to actually see how we use Euler's formula. In examples, you may be given a certain amount of information, but asked for another piece of information. So you just have to recognize you're using that same formula for all of these. So remember, F plus V equals E plus 2. So F is what I'm looking for here, plus V is 20, equals E is 30, plus 2. So F plus 20 equals 32. going to subtract my 20 from both sides, and I find out that my faces must be 12. Now what's interesting is this polygon, or this polyhedron here, a 12-sided polyhedron, is called a dodecahedron. That's something that you should definitely know. A 12-sided, 12-faced polyhedron is called a dodecahedron. So then you go ahead, you try that next problem. We can also use Euler's formula with what we call nets. This is an example of a net. We're going to take a look at how Euler's formula works with it. Now what's different though is instead of f plus v equals e plus 2, when we're dealing with a two-dimensional picture, it's f plus v equals e plus 1. So it's really important to note. If you see a net, you cannot use that same formula because it's different for a two-dimensional picture. So the other thing that's different is f is the number of regions in a 2D instead of faces. So it's a similar idea, but it could be a little bit different. Your vertices are still vertices, which remember is defined by 3 edges coming together at a point. And then our edges in 2D are just segments, but it's only the segments that link the vertices. So that's also important. It's not going to be every single line on that picture. It's going to be just the ones that are linking together your vertices that are formed. So let's look at this first example. I'm going to count up my faces, my vertices, and my edges to plug them into Euler's formula. So my faces are easy. I've got 1, 2, 3, 4, 5, 6, 7, 8. So let's write that down. F equals 8. And then we've got our vertices. Now this is important because I'm looking for the corners within this picture, but it's got to be a corner where 3 or more lines come together. So like this one doesn't work over here in this corner. This one doesn't work, but this one does. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I get 10 total vertices. And now I have to go back and do my edges, which is arguably the hardest thing to do because you have to think about which lines create those vertices that we were just counting. It's like this segment here does not create a vertex. This one does, and this one does. They all meet at that vertex right there. So let's start counting. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there are 17 edges. Now if we plug it into that formula, f plus v equals e plus 1 because it's two-dimensional. I have 8 plus 10 equals 17 plus 1. And that is in fact true. So you can see that it's going to be a little bit different, but Euler's formula still does apply to nets. So I need you to do that U try right here. And the next thing we're going to talk about is what a cross-section is. A cross-section is where you have a 3D object, but you're essentially taking like a very, very thin slice of that shape. So you can imagine taking a piece of paper or even a knife and just kind of going through that shape and seeing what is going to happen. For example, like if you take an orange, you have a sphere. If you cut it in half, if you take a slice of it or a cross-section of it, you now have a circle. In this example here, we have this triangular prism, and if you take a cross-section of it, you have this triangle right here. So a cross-section is the intersection of a solid and a plane. The plane you can think of as that knife. So here we've got an example that we're going to look at. It's asking what the cross-section is using this plane and the solid at the right. So you see that you have like a cylinder here, almost like a Pringles can or a can of Monster. And if you take that and you take a cross-section going across the length of that can, you're going to end up with this shape here. So you can see that you have a rectangle. So like if you think about taking a can of Monster and just slicing it in half, what results on that flat edge is a rectangle. So I want you to think about this problem down here, this you try, and bring that with you to class.